All right, so let's look at the first of three kinds of calculations you'll be asked to know about, or I want you to know about acid-base equilibria. And all these are acids, but you could do the same thing with a base, right? It's the same equilibria. So I think there might be an example of a base on the worksheet, but right now we're going to work with acids. And I think in general, it's more common that you work with acids. So what if I have a certain concentration of acid, and a weak acid, and I take its pH? Is there a way to calculate the Ka? As I said, of course there is. The key to this is recognizing that this pH is going to be that's the negative log of the hydronium ion concentration, right? When you dissolve 0.250 molar HF. And so that's going to represent the equilibrium concentration of the hydronium. Right? This pH is going to be the negative log of the equilibrium concentration of hydronium. Let's scroll down and see. So you write as usual, you have a weak acid, you're going to write the equation for the dissolution. Right? It's going to make H3O plus and F minus. And then you do your ice table. Well, initially, all there is the HF. There's no hydronium and no fluoride. Now, I have a little star there. I'll talk about that in a second. But what's going to be the change? Well, you know this is a case where since there's no product, you don't have to worry about Q versus K, right? You know it's going to go toward the product side. So the reactant side is going to go down by X, and these guys are going to go up by X because it's a 1-to-1 mole ratio. The equilibrium concentration is going to be 0.250 minus X of the HF, and then these guys are going to be X and X. But when you think about the information given, as I mentioned, this H3O plus concentration at equilibrium is going to be what you took the pH of, right? You dissolve this, it went to equilibrium, you stuck a pH meter in there, and you got 2.036. So there's actually a way to find X. This application is fairly easy once you write the ice table, because then what you're going to do, recall that, to get the H3O concentration from pH, it's 10 to the negative pH. Again, so in this case, let's find that H3O concentration, and this is going to be equal to the X, right? So the 10 to the negative 2.036 is 9.2 times 10 to the negative third. So that's what this is going to be. And of course, the fluoride ion concentration is the same. And so then what do we always do? Remember, you always write your equation, and you always write your K expression. In this case, again, we're going to call it Ka. So the Ka is the hydronium times the fluoride over the HF. Well, that's going to be X times X over 0.250 minus X. Well, we know what X is. Plug it in. All right. And you get that Ka is 3.51 times 10 to the negative fourth. That's just doing the math. And just for the heck of it, I took the negative log of that to get the pKa. I don't think I asked that in the initial prompt, but they may ask you to find the Ka and the pKa. Well, finding the pKa is pretty simple. Again, anytime you take the negative log of something, you're going to call it the p. All right? So pKa. That means the negative log of the Ka. And then you end up with these interesting relationships as I scroll down. Remember how pH plus POH equaled 14? It turns out, and we will see how this evolves as we go through this. It turns out that, and this is just an amazing kind of relationship, but it has to do with properties of the equilibrium constant. And if you wrote this reaction in reverse, right, anyway, it turns out that pKa plus pKb equals 14. So what I could do is I could subtract from 14, subtract this Ka from 14. Find the pKb, but what's it the B for? What's it the pKb for? It turns out that will be the pKb for this guy's conjugate base. So if the reaction went in reverse, F minus plus H3O became water and HF, okay, that equilibrium constant would be Kb, right? And so it ends up that it turns out that an equilibrium constant for that direction is called Kb, and from Ka you can find pKb, and then 10 to the negative Kb, pKb would be the Kb of that conjugate base. So there's all this kind of intertwined relationships mathematically. Okay, now we're going to look at the second application, which would be calculating the equilibrium concentrations of hydronium, or in this case hydroxide if it's a base, given the Ka. Again, there's an 8-step process that you want to go through, and we are going to go through these 8 steps sort of one at a time, using the example of HCN being dissolved in water. So here's this type of problem. You're going to be given the Ka, and you're going to be asked to calculate the pH of this solution with the concentration 0.10 molar in this case. To find the pH, you need to know the equilibrium concentration of hydronium. Yes? And then you take the negative log of it. So the first step, though, is recognizing that, hey, you know what? When water dissolves, when water is just sitting there with itself, right? Isn't there this reaction that says water interacts with itself to make hydronium? Remember we talked about that last semester in Unit 4? Okay. And so if you remember on that previous problem, I had a little star next to the 0 of the initial concentration of hydronium. Well, if the HF was dissolved in water, that water had 1 times 10 to the negative 7th concentration of hydronium, right? Because any glass of water, right, any water has some hydronium in it already, because water reacts with itself, right, to make a little bit of hydronium. Yes? In that equation called the self-ionization of water. So, like looking at this equation at the bottom of the slide, you know, H2O plus H2O, they collide, right? And then one of the hydrogen goes to the other water and makes H3O and leaves O minus, okay? OH minus. That also has an equilibrium constant that we know was 1 times 10 to the negative 14. Yes? You hopefully recall that, and was called Kw, right? The equilibrium constant for the self-ionization of water into hydronium. And I guess the point I want to make here that you have to consider is, well, there are 2 things in your beaker, right, that could act as an acid, HCN and water. Okay, and also remember, water can act as its own conjugate base, right? But anyway, there are 2 possible proton transfer reactions. So step 1 is look at your equation, identify everything that can be an acid. Well, the acid and water. If it were a base, it would be the base, and water would be the other base. Okay? So you have to write those reactions, and next to them you write the Ka. Okay? Now you and I can already kind of see that isn't HCN going to be a much stronger, well, not a much stronger acid, but it's going to be a stronger acid than water, isn't it? How do we know that HCN is going to be a stronger acid than water? By looking at what's on the slide.
Higher Ka.
Yeah, higher Ka, right? So that is what we're going to call the principal acid-base reaction. Because if you think about it, this guy is going to be producing most of the hydronium that's in your ending solution, right? Because it's the acid and it has the higher Ka. That's a pretty low Ka for an acid. This is actually a really weak acid. A lot of them are 10 to the negative third, fourth, fifth, right, sixth. But this is 10 to the negative 10. So HCN, hydrocyanic acid, is not very strong. But it's stronger than water. And so you call this the principal reaction. And then the water reaction would be called the secondary or the subsidiary reaction. It's going to maybe produce a little bit of hydronium, but the major producer of hydronium is going to be HCN. All right? So see how those three steps can kind of almost be all done at once, because you're going to write this reaction number 1 here, HCN plus H2O, and you're going to recognize that H2O could also produce some hydronium, right? But then you're also going to know that this guy has a bigger Ka than water's Ka, which is negative 14. All right? And so you can almost roll steps 1, 2, and 3 together, knowing that HCN will be the stronger acid. Got it? So like I'm saying, there's 8 steps, but okay. Because HCN is the stronger acid, you are going to assume that basically the H3O that appears right at equilibrium is going to be due to the HCN. But again, that's what this little star here is on the initial concentration of hydronium, right? We know that the water has produced a little bit of hydronium by itself, but we just call it 0 because think about this. It's 1 times 10 to the negative 7. And the concentration of HCN is 0.1 molar, 0.10 molar. Well, with sig figs, right? Remember, this is very small related to the number of sig figs of that concentration. Yes? So it's negligible, so we're calling it 0. Okay. Again, 1-to-1 to 1-to-1 mole ratio. So the acid's going to go down by X, H3O and CN minus are going to go up by X, and so the final concentrations at equilibrium, 0.10 minus X, and then X and X. And here's one of these cases. In these acid-base equilibria, you're going to assume that X is very small with respect to the initial concentration of your acid. Okay? Now, in the end, if you find out that the X's concentration, this X, okay, is greater than 5% of 0.10 molar, then you can't make this approximation, and you'll have to use a quadratic equation solver to solve it. But the College Board's not going to give you one of those because they're not going to ask you to solve one that uses a quadratic equation solver. Okay? So that all of these are going to be able to be solved using this approximation. But again, if you find that the concentration of X is within 5% or more of the initial concentration of your reactant, then you have to go back and use a quadratic equation solver. And I've done problems like that, believe it or not, in my life, and it does make a difference to the final answer if it's greater than a 5% of the initial concentration. So you would. Okay. So, but again, making that assumption that that HCN's concentration is just going to be still 0.10 minus some extremely small number makes the math easier. Okay, so here's your Ka, just like we did in this case. This is just like we did steps 4 and 5, or just like we did with unit 7. So you write, so that's X, so it's X squared over 0.10. Again, assuming that. And then you solve for X, and you find that X is 7 times 10 to the negative 6. Okay? And so that is, look at that, that is very small with respect to 0.10, so the assumption was good. The assumption that X is very small, that is not within 5% of the value 0.10. Okay? Now, it asks for this question asks for the concentration of everything at equilibrium. And so this is where these next steps are going to go. Step 6. What is the concentration of HCN at equilibrium? 0.10. So these are the equilibrium concentrations. And then these two guys have a concentration of 7 times 10 to the negative 6 molar. Now, though, there often you have to find out, well, what is going to be the concentration of this OH minus? Okay, this is a good one. because you know that there is some OH minus in here because of water. But think about this. When HCN produces a hydronium, it's producing a common ion to the second subsidiary reaction, isn't it? If the first reaction and this reaction are going on in the same test tube, and the first reaction produces hydronium, which way is this second equilibrium going to go? To the left, which means we know that the initial concentration of hydroxide in water is 1 times 10 to the negative 7, right? But the production of hydronium by the first reaction affects the second reaction, drives it in reverse, and so this concentration of hydroxide that was there naturally actually will go down. And there's a way to calculate that. So you might be asked to calculate the remaining hydroxide ion concentration from the subsidiary reaction. And if the question says calculate the equilibrium concentrations of all species present, then you have to do this step. If it just asks for the concentration of hydronium, you don't have to do this part, right? But if it asks for the concentration of all species present, well, on the right-hand side here is all the species present, well, with the HCN at equilibrium. Okay, so what do? Let's scroll back down and see what those last couple steps are telling us. Well, you know that this equation is, so we're working with the subsidiary equation, and this is the equilibrium equation, right? The equilibrium expression for water, right? Kw, it's called Kw, H3O times OH minus is 1 times 10 to the negative 14. But now this is kind of like a common ion thing, right? So what do? You substitute this concentration of H3O because it's no longer 1 times 10 to the negative 7. It's 7 times 10 to the negative 6. And that's going to cause the hydroxide ion concentration to go down to 1.4 times 10 to the negative 9. And this Kw equation, which is the equilibrium constant for the subsidiary reaction, right? Or sorry, equilibrium expression for the subsidiary reaction, can allow you to calculate the new OH concentration. That's kind of cool. All right? So the concentrations of all the species, HCN, 0.10 molar, H3O and CN minus, 7.0 times 10 to the negative 6, and the concentration of hydroxide will go down to 1.4 times 10 to the negative 9. Yeah, Ben. Yes, you can. Yes. I'm glad that's on videotape. All right. And then step 8 is calculate the pH. So all of that in order to get a lousy pH of 5.15, right? But how do you find the pH? Well, you take this concentration of H3O, 7 times 10 to the negative 6, take the negative log of it. You good? So the difference in this one is from other equilibriums that we did, questions like this that we did in Unit 7 is, it's not just one reaction going on, right? There are 2 reactions going on because water is pesky enough to be reacting with itself and making a little bit of hydronium and a little bit of hydroxide. Okay? So that's the difference with acid-base equilibrium. Now, scroll that up so you can see. Okay, so again, calculating percent dissociation. You have, you know the initial concentration of your weak acid. You've calculated the amount that is dissociated into H3O plus. And that's going to be the numerator because remember, all percents are part over the whole times 100. So it's the part that creates H3O plus, that is ionized into H3O plus over the initial concentration, right? And then times 100. So in this case, the equilibrium concentration of hydronium is your numerator, because that's how much has dissociated. And you're dividing that by the initial concentration, which was given, 0.10. And you see that the percent dissociation is extremely small, 0.007%. because that's, so this would be 0.00007. So 1 in 0.00007 of these HCNs have dissolved, right? Okay. And so if you kind of think about that, you know, when we draw our beaker, like I was drawing the beaker with HF, I was trying to show you the dissociation. Think about this. What this means is at equilibrium, it's like almost all HCN. And then 7 out of, what is that, 10,000, 100,000? 7 out of 100,000 of those HCNs has disassociated. Yes? Eh? And so when we say that this is a weak acid, we mean it. Right? 7 out of 100,000 of the HCNs has actually created H3O. That's kind of what that's saying. So yeah, it's almost all on the reactant side. Okay, so that kind of wraps up these 3 applications, right? Finding the Ka of something if you know the pH and the initial concentration. Finding all of the concentrations at equilibrium given the Ka, and then finally an offshoot of that second type of application would be calculating the percent ionization or percent dissociation, right? And this percent dissociation, you can look these up online, all right? So that's it for this.